Greetings. In this one we will be discussing the method of variation of parameters, and I will be deriving a formula for solving a second order inhomogeneous ordinary differential equation using variation of parameters. So why do I derive this formula? You'll see while we go through it, but let me just say what I'm actually talking about. I said ordinary differential equation, that means there won't be partial derivatives. All the functions inside our equation will be only in terms of x. It could be also t, but I'm choosing the variable to be, the independent variable to be just x. So that's my choice there. So the equation, let's say, namely is exactly y double prime plus, and that's of x, I mean of x, plus a of x times y prime plus b of x times y equaling c of x, let's say. So this is the equation we are talking about. And now the point here is that I keep saying, and by the way, this also will be y prime of x, y of x, so it's not confusing. So we're not like sometimes saying of x, sometimes not saying of x. I always mean this in respect to x. This is the first thing to keep in mind. But what I'm actually going to be doing is I'm going to make it all simpler. I'm going to make it all shorter to write in order to save a lot of space and time from our calculation here. So the point is that instead of y double prime of x, I'll just say y double prime. Because everything is in respect to the same variable, namely x. I am just using the shorthand notation without the parentheses and the independent variable explicitly mentioned over and over again. The same for a, the same for b, and the same for c. So if I shortcut it all, I will get this. Y double prime only multiplied by a constant multiple of 1, so the default multiplication of it. Then a times y single prime plus b times y without derivation, and then c. And y is the function we are looking for. So y of x, f of x, however you want to call it, I'm calling it y. It's probably the most usual way to approach the name of a function with ordinary differential equation, especially simpler ones. You know, one independent variable y is the most common letter for that. And so we are working with this. This is exactly the same as I wrote here. But here I wrote it quicker and simpler. But all along, I mean all these letters, all of these, y, a, as well as b and c, are functions in respect to x. And the function that will be the solution to this differential equation that I'm looking for is y. So I'm looking for y. No. Now to get rid of the confusion, potential confusion, let's go to read this previous slide. And we can start focusing on the calculation itself. So I said we were going to be introducing a method called variation of parameters. And there is something called homogeneous and inhomogeneous ordinary differential equation. If it's homogeneous, that means that we would have a zero on this right side. And the way to solve it is also systematized. There's something called the auxiliary equation, and basically the solution will be in terms of sines, cosines, or e to some power of x. And so, and the linear combinations of e's in of such functions, exponential functions. And that's that. And if we have an inhomogeneous equation, well, that will be all the solutions solved through the ways set out for homogeneous differential equations, ordinary differential equations. But we are dealing with an inhomogeneous one, inhomogeneous case. That means instead of the zero on the right side, it's equaling some function, also of x. And I call that c. And don't mistakenly c1, c2 as constants that we will be talking about in a second. So when I'm talking about variation of parameters, it's one of the several different methods for ordinary differential equation solutions. And with other methods, we had a concrete example without some arbitrary a, b, and c as the multiplication factors for the first derivative and the function itself, and then something on the other side. We had some concrete example, for example, when we were talking about some other method of solving ODEs, ordinary differential equations. But this time, we are actually deriving a formula, because once you have this formula, you can repeatedly use it. I will derive a formula for equations like this, where you have a second derivative plus some function times first derivative plus some other function or the same one. A can equal to b, but they don't have to. That's why they're called different letters. It can turn out, or I can have it in such a way, or I don't have to. Plus some function of x times y itself equaling some function, some third function. So that's my equation and I will get a general solution. And now let's start with some theory intro that is good to know before we continue to the variation of parameters themselves. Because ordinary differential equations have this property that there's always two parts of the solution. There's the solution for the homogeneous equation. So even if we have an inhomogeneous solution, the magical thing about it is that we first just solve for equaling 0. And then to that, we add the so-called particular solution, which is based on what is on the right side. What is that function on the right side? So even if it's inhomogeneous, it doesn't mean that much. Some basis of the solution will be the same. And then to add that, we add something more. So for a second order differential equation like this, let me start deriving the formula for variation of parameters. I know that when I solve the homogeneous case, which I'm not going to go into, it could be, for example, namely if if A and B were, for example, constant numbers and so on, a potential solution for equation of this type would, for example, be y equals some constant c1 times any constant c1 times e to the x plus c2 e to the minus 2x. That could be a solution. So we have e of x, e to the x, e to the minus 2x, linear independent, and all the linear combinations make up the solution space of this differential equation. So basically any function of this form is a solution to it. Any linear combination of these two functions, where c1, c2 in the reals are any constant multiples. But variation of parameters says this thing, and here it comes. Variation of parameters says, take the solution that you have for the homogeneous version, like if c was 0, and then take it, and also take it including the constants, but imagine that the constants are a function of x. So they're not just constant, but c1 of x, c2 of x, as we have here. So just like this was a concrete example, let's have a general example for such an equation. So for this equation, the homogeneous version, if there was a 0 on the right side, there's first this general solution, which is part of the solution. And it will be namely y, and it will be in the form c1 y1 plus c2 y2. So y1 of x, y2 of x, and c1 are not of x, they're just constants. But now I start with variation of parameters. We want to derive the formula. And the way I'm going to face it is, I will say that I now want to look for the remaining solution, which we will add to this one, and that will mainly be yielded in such a way that I start looking at c1 and c2 as functions of x, as I said before a moment ago. So usually people now, when they do the variation of parameters, you can find in literature when you're learning about this, the c1, c2 will be renamed to u1, u2, and treat it as functions of x. What I can also do, I can choose whatever name that's possible to choose. Whatever name possible, c1 of x, let's say, and c2 of x. I'm just adding the x to make it here again, right? So I'm now not talking about c1 times y of x, but I'm actually really talking about c1 of x times y of x plus c2 of x times y of x, y2 of x. So I change the constants into functions of x. So I now don't view these multiplication constants in this linear combination as constants, but I view them as functions of x. And now I will work with it. And what I will mainly do is, I will take this, and this might remind you of the method with determining coefficients, which is a method that you would use for a similar equation, for this type of equation actually, exactly. For example, if we had some equation, we got some results in terms of those e to the x, e to the 2x, whatever, and on the other side there will be some linear function equaling to it, we need that particular solution. So first we would take this thing with the normal c1, c2, and plus and add, that's the solution, but to the solution we add yet another term, which will be based on what is on the right side. And then we basically create like a model of the right side in a more general way, and we substitute it back into the equation, and then from that we yield the second solution. Then we add everything up, and that's the whole solution. We're doing a kind of similar thing here, not completely similar, but it is in a way similar in such a way that we look at some expected solution and we plug it into the equation, substitute inside. So what I said is, I had this c1 y1 plus c2 y2, but then I decide C and C1, C2 are functions of x, and I want to take the derivatives, and of course I need the first derivative as well as the second derivative, and then I will plug them back into this equation. So I will mainly do first derivative. If this is, and again, simplification purposes, I am really going to do C1y1 plus C2y2, but don't mistake it. I really do not mean it's C1, C2 have nothing to do with this C. This is C of x, another C. So we have C1 of x, C2 of x, and C of x. Coincidence of chosen notation, but it doesn't mean anything more than that. But C1 and C2 would be usually constant, but now I start treating them as functions. So I will put primes above them as derivatives and so on. Now I'm going to do y prime and y double prime, so I can substitute it back into this equation. A and B will stay the same as well as C. So what do I do? Product rule. C1 prime y1 plus C1 y1 prime, y1 prime. C2 prime y2 plus C2 y2 prime. Now, here is a trick used for variation of parameters. The trick says the follows. The terms that contain the C1 prime and C2 prime, the derivatives of these newly established constant functions, or they're not constant functions, they're functions that multiply the y1 and y2 from the general solution. These two terms I set equal to 0. So for the rest of our calculation and the formula derivation, it will turn out to work. It will turn out to work. I will use this condition all along. C1 prime y1 plus C2 prime y2 equaling 0. And we will eventually refer to this. We'll refer back to it. So I'll use that. That means I cross these out. From now on, I treat these two terms as 0. And together, when I add them, they're also 0. So only this is left for the calculation of y double prime, therefore. Because these are now treated as 0. So I will have, for that y double prime, have C1 prime y1 double prime plus C1 prime y1 prime, to be careful, and then I have C1 y1 double prime plus C2 prime y2 prime plus C2 y2 double prime. So that's my y double prime. All right. And again, don't mistake y with y1 or y2. All these three things are different functions. Just like C1, C2, and C. Different functions. Alright? Alright, so we got these expressions. Y double prime and y prime. Well, y we had already. We set that out. We started with that. Y prime and y double prime we got. We substitute it now back into this equation. So hopefully there'll be enough space for it. Well, let's see, we'll be right. I'll write it here on the left. So we'll have, well, there's constant multiple of 1 for this term, there's a multiple for y prime, so I have to be careful about that, not to forget any power amount. So basically, y double prime first, that's gonna be C1 prime y1 prime plus C1 y1 double prime plus C2 prime y2 prime plus C2 y2 double prime. Alright. And then, to that I add plus, and so I can now delete it because it takes so much space. We have it. To that I add a times y prime. Y prime is what is left. We cancel the C1 prime y1 and C2 prime y2. So this is left, namely C2 y2 prime and C1 y1 prime added together. And then plus b times what y is this. Without any derivatives. Alright, and all is equal to C. And again, C1, C2, C here is equivalent. They're all different from each other. Right. I mean, I remember this, so I can delete it. We'll see. We won't confuse anything for the rest of this process here. So now I can continue with this, and now we're already getting somewhere. We're trying to derive a formula such that we find the u1 and u2 eventually, and then we plug it into the u1, u2. I mean C1, C2. Regarding the choice of notation here, I chose to call the two multiplicating functions of y1 and y2 respectively C1 and C2. So that's the naming we use here. But now, let me just write this here. So I'm working with this the whole time. C1, Y1 plus C2, Y2. We are looking for the C1 and C2. And the way we're going to find it is with this equation now. And also with this condition. So these two equations are now going to be used. But there's a thing that might not be visible on the first glance, but it's very important to simplify this expression now. I will start with multiplying everything out first, and then I will note that pattern. So let's multiply everything out, even if it takes a little bit of time, right? It's always good to experiment and try different approaches to even with these algebraic manipulations or anything. Like by time, then after some time of maybe repeating these kinds of things, you get a better intuition or better feeling for what makes sense to do or what doesn't. But let's just view it as to try it all out. So basically, I multiply everything out. And now I will be able to identify exactly this in this equation 2 times. And I know that should be equal to 0. So the homogeneous solution C1y1, C2y2 should be equal to 0. And so once I find it here somewhere, I extract it and I can cancel it out from this equation. And thereby I will get rid of it, so that this equation simplifies a lot, this whole expression. So, namely, the way we can find it is we should identify how this equation looks and try to find, for example, first let's find y double prime plus ay prime plus by inside this equation. All three will be multiplied by some one other constant, and namely, for example, in this case it will be C1. So if I isolate C1, I will really get, I can find a times, and this is a fact that is observed here, and that's very useful. So let me see C1 y1 double prime. So that's the first thing. I already have the first part. I just want to fulfill this whole equation to get a 0 factored out of this expression. Then we want a y prime. So that's this one. If I factor out the C1, right? A y prime. And then I want by. So I need C1 by. That is somewhere, it must be somewhere here. C1 y1b. Alright. So by1. This is also some 1. We have to be careful about that. Alright. So what we know is for the homogeneous solution, y1 is a solution, y2 is a solution as just like all their linear combinations, but y1 on its own and y2 on its own are both solutions, of course. So this must be 0, and then we can also get the same thing but with y2. And namely, that will be associated with, let's see, C2. We will have C2s that are associated with it. So we will get some, we will try to factor out, but we were actually only factoring out we factor out the C1s that were not derivative. You see, we have some C1 derivative here, and we have also a C2 derivative here. But in the end, throughout those will be all the terms left equaling to C. And so everything will simplify so much. So C2 should be now multiplied by y2 double prime. So this is the second individual solution of the two that were put into the linear combination in the y equals C1 y1 plus C2 y2 that we saw in the beginning. Y prime should be also possible to find, plus y2 prime, and now we need by. So let's find C2 by2 prime, or actually C2 by2. So plus by sub 2 times C2. So this one. So we factor out these two. These two should become 0. Because they're this equation exactly, and we put the homogeneous solution inside it, and then we have only these two things left of everything. Let's see, C2y2, y double prime. Oh, I just didn't cross it out. So these two things are left. This one and this one. These two should become 0. So I will add them. So namely, C1 prime, Y1 prime, plus C2 prime, Y2 prime. And it all equals to C. Well, again, C1, C2, and C are three different things. Don't get confused about it. So this is 0, and this is 0 for the reason I stated. Doesn't matter, they multiply by C2 and C1, they are 0 on their own. So the whole term goes to 0, and this is what is left. So here we are finally getting to the very end. We're getting very close to the actual conclusion of everything. So we can now get rid of this and get another step further. I will just sum up here the two equations we have access to now. So we have C1 prime Y1 prime plus C2 prime Y2 prime equaling C. Once again repeating C1, C2, C are three other things. I can delete this, repeat it over here on the left, and these two equations I will now use to solve for C1 and C2. That's what we need. And then we will plug it into this. So once we plug it into this, we will get, so when C1, Cx, once we find it, we will get the particular solution, depending on what our C1 and C2 is, in terms of the rest of things. Alright, so let's see. It will be really in terms of Y1, Y2, and C. Alright? It won't be in terms of A and B, those were lost. Alright. We don't have A and B's in this system of two equations. Alright, so I would start with the equation that has a 0. So C1 prime Y1 equaling minus C2 prime Y2. Let's be careful about everything so there's no mistake in here. Minus C2 prime Y2 over Y1. So C1 prime is minus C2 prime Y2 over Y1. But now I will have to plug it into this second equation to get C2. So I'll plug it into the second equation. So I know C1 prime is this minus C2 prime Y2 over Y1 prime plus C2 prime Y2 prime equaling C. We can factor out C2, so we get Y2 prime minus so we have C2 prime, so Y2 prime minus Y2 minus Y2 Y1 over Y1, alright, equaling C. And now before I divide both sides by this parentheses, I will bring these two to the same denominator. So I will do C2 Y2 prime Y1 minus Y2 Y1 prime over Y1. Alright, equaling C. And so C2, we should be careful because this is C2 prime all along. C2 prime is equal to CY1 over this. So Y2 prime Y1 minus Y2 Y1 prime. So this is it. So C2 prime. Alright, and then so C1 prime will be actually very similar because we have we are putting in this C2 prime from this expression into here, and so we have basically minus this, but we divide it by Y1 and multiply it by Y2. That's all this does. So it's minus C Y2, but the bottom is the same. Y2 prime Y1 minus Y2 Y1 prime. Alright, so we got C1 prime as well. So now we finally go to the final part. In the beginning started with what we began was this expectation. Y was going to be equal to C1 Y1 plus C2 Y2, where Y1 Y2, the solution for the homogeneous case already we got them before. C1, C2 are functions that multiply. And so, I have solutions for both C1, C2, and now I can just make the formula whole by it. And so, namely, that will be exactly this. Y, and I will do Y sub P as particular, that the solution is not for the homogeneous equation when there is 0, but also take into account the C, so the other part, that as I mentioned in the beginning. And that is namely C1, Y1 I'll just rewrite it once again, plus C2 y2, and then I plug in this stuff. But I have to integrate it. And everything is with respect to x, as I said, so it will be an integral dx. So to get C2, I integrate this, and the same for here. Just integrate it, dx, and dx here as well. So there will be big integrals there, and it will depend on the values of y1, y2, and c, how these integrals will be to calculate. It might actually not be that easy, so that's a thing to always expect. All right, so let me put it there. Namely, it's minus. I can put out the minus out of the integral. So this is minus c. I don't mean c1 or c2. It really is this here on the right times y2 over y2 y1. y2 prime y1 minus y2 y1 prime. And this looks a lot like some determinant, and I will mention it in a second why. Dx times y1 plus, and now c2, the integral, I'm multiplying by this integral to y1, and then c2 is this integral c y1. So for C2 we have y1 inside the constant integral to constant, and then the bottom, the denominator is the same. So y2 y1 prime dx, and then multiply by y2. Alright, and then this is also like the whole thing is multiplied by y1. So y1 and y2. So this is our final expression. So all the work so far was used to only get to these expressions. And we can have an example of it. For example, I mean, I can delete these because we have it all contained in this formula now. So this is basically the formula where we only need to know C, y2 and y1 for the homogeneous solution. So you will have to take the A's and B's into account before having the y1 and y2 first. We didn't take a concrete example where we would have the y1, y2, and first have to calculate those and then continue. I mean, I can give a concrete example. For example, we could have y double prime plus 2y prime plus y equaling 2. But first I do the homogeneous version, so first I do it as 0 on the right side to solve for y1, y2. This equation is fine when I'm solving for y1, y2. And so I use the auxiliary equation, which is basically when there's second derivative, it's the square of r, which r will be used in a second. And again, this is a thing I described in a previous video. So this is already covered. This is not the matter of interest in this one. We're just going quickly through it. You get an auxiliary equation. You might spot this pattern or might not spot. I'm doing it quite quick here. But then from this, there's this theorem that there's two solutions depending on the two values of r. I mean, if the value of r ends up being complex, then we get sine and cosine. And then the linear combination, the C1 times this plus C2 times this, will be the solution for the homogeneous case. Or in the case it is complex, which this is r plus 1 times r plus 1 actually. So this is repeated roots. So actually in this case, the solution will be yet slightly different, but it would contain the exponentials. But not to get too distracted here. My point there was just this is an example solution, so I will get the y1, y2, which will be this e to something, depending on the exact scenario of the equation. And then c1, c2, I start looking at them as constants. Then I get all the way to this expression. Now again, I still know that this is c of x, this is y2 of x, y2 prime of x, and everything is of x, but I just didn't write it all along because it would take so much space for writing. And now we go here, and with this formula you can get the particular solution that you will have to add. So first, the solution as I illustrated here, I didn't complete it or exactly show it, but like the general solution for the homogeneous case of the equation, and then plus yp. That's the whole solution for an equation that also has c on the right side. And let's consider a concrete example. So let's say that whatever a and b are, the y1 is e to x and y2 is e to minus 2x, then you take them and you put them in this equation. Derivate them accordingly, put it in the equation. Also confront what c is on the other side. Let's say c, this function on the right side would be, for example, sine x. You also confront that here, sine of x. And then you put it all into this integral and you get the particular solution. So you get the constant, you would have to calculate this whole integral. For example, what integral would that be? Integral sine x e to the minus 2x over, and then you would have to derive y2, which would be minus 2 e to the minus 2x times y1 e to x, and then subtract y2, which is plus 2 e to the minus 2x, because it should be minus. But actually, it's not derivative, so that's a mistake. Once again, subtract it simply. It was a mistake because there's no derivative now. So y2 is really minus e to the minus 2x, and then multiply by y1 prime, which is just e to the x, is not changed. And then you will have to do all of this dx to get just the c1. And you see, you might find out it's too hard to integrate, or maybe it's not too hard to integrate depending on the case. This one doesn't look that easy to integrate, honestly. So a lot of times it might happen that the integral is almost undoable or completely undoable by hand, for example. And now let's just observe one last thing about this whole thing. We didn't do a complete example, which we might do in another one, but let's look at one last thing here, and you might notice here, y2 and y1, they look like, this is like a result of some determinant. And indeed it is. It's called the Wronskian matrix, and also the determinant might be just called Wronskian shortly, or the determinant of the Wronskian matrix. And the Wronskian matrix, what it basically is, we can just show it right here. When we have, it is an n by n matrix, so a square matrix, composed of functions in the first row, and then below in the respective column of that function we have all its derivative till the matrix is filled, and it's a square matrix. So if we have two functions like here, y1, y2, each of them will only get one derivative in this matrix. So you get y1 prime, y2 prime, this matrix. And when you take the determinant of it, you get y1, y2 prime minus y1 prime, y2. And this is exactly what we have here. So you see, the determinant of this so-called Wronskian matrix is exactly the denominator in this, inside this argument of the integral, of both of the integrals. So this Wronskian matrix is basically the matrix of, the first row is the functions we consider, and then below we put the derivatives. I mean, this can be extended to n by n to anyhow big square matrix. If we have three functions, we would have y1, y2, y3, and then for each of them we have two derivatives. So the first derivative first, and then y double prime, y2 prime, y2 double prime, y3 prime, y3 double prime. And then you would take the determinant of the whole thing if you wanted the determinant of that. But in any case, we were only considering second order differential equation, which as we see has two fundamental solutions in the homogeneous version. Then we take the linear combinations, and out of that we also extracted an expression for this particular solution with the method of variation of parameters.